A train horn cuts across a quiet crossing. At first, it sounds sharp and urgent, as if the note itself is climbing. Then the engine rushes past, and in the very next moment, the same horn seems to fall into a deeper tone. The train driver has not changed the whistle. The machinery has not suddenly played a different note. The change happens in the space between the moving train and the listener. This is the Doppler effect, a change in the frequency we receive when a wave source and an observer move relative to each other. Sound travels as a sequence of pressure waves. Each wave crest leaves the horn and spreads through the air at the speed of sound. When the train is moving toward you, every new crest is released from a slightly closer position than the one before it. The wavefronts arrive crowded together. Their wavelength is shorter, so the frequency you hear is higher. To the ear, higher frequency means higher pitch. After the train passes, the geometry reverses. The horn is moving away. Each new wave crest begins farther from you than the previous one. The wavefronts are stretched out, the wavelength becomes longer, and the received frequency falls. The horn sounds lower, even though the source is still producing the same frequency. The size of the shift depends on speed. A walking person barely changes the apparent pitch of their voice. A fast train, an ambulance, or a racing car produces a larger shift because the source moves a significant distance between successive wave crests. If the source could move at the speed of sound, the wavefronts would pile up dramatically. Beyond that limit, the result is not just a change in pitch, but a shock wave, the physical basis of a sonic boom. A common mistake is to think the Doppler effect is only about sound. It is broader than that. Light waves also show Doppler shifts. When a star moves away from us, its light is shifted toward longer, redder wavelengths. When it moves toward us, the shift goes the other way. Astronomers use this to measure the motion of stars and galaxies. Doctors use a related principle with ultrasound to measure the speed of blood flowing through vessels. The key idea is not that the sound itself changes after leaving the horn. Each wave travels normally once produced. What changes is the spacing of the waves that reach the observer, because the source is moving while it sends them out. So, the passing train gives us a small experiment in every wave in the universe. Motion does not merely move objects through space, it also changes the rhythm by which their signals arrive.